When we imagine a rock from outer space crashing to Earth, our minds often conjure images of a glowing, red-hot object setting fire to everything it touches. This is a common scene in movies and television, but the reality is far cooler. In fact, when a meteorite finally ends its long journey and lands on our planet's surface, it is typically cold. Sometimes, it is so cold that it might even be covered in a layer of frost. This might sound counterintuitive, but the physics behind this phenomenon is quite fascinating and reveals just how extreme the environment of space truly is. The journey of a meteoroid through Earth's atmosphere is incredibly violent and brief. As it plummets downward, friction with the air heats its surface to thousands of degrees, causing it to glow brightly as a meteor, or what we call a shooting star. This intense heat, however, only affects the very outermost layer of the rock. This layer is rapidly stripped away in a process known as ablation, which effectively acts as a heat shield, carrying the extreme temperatures away with it. The entire fiery passage through our atmosphere lasts for only a matter of seconds, which is not nearly enough time to heat the object all the way through. Before its brief, fiery encounter with our atmosphere, a meteoroid has spent millions, or even billions, of years traveling through the frigid vacuum of space. Out there, far from the warmth of any star, its core temperature can drop to unimaginably cold levels, around -270 degrees Celsius. This deep, penetrating cold is not something that can be overcome by a few seconds of atmospheric friction. After the initial burn, the meteorite slows down significantly and spends its final few minutes of descent simply falling through the cold upper atmosphere, allowing its surface to cool rapidly before it ever reaches the ground. We have real-world evidence to back this up. In 2007, a meteorite crashed through the roof of a house in New Jersey and was found to be at room temperature shortly after impact. An even more famous case occurred in 1955, when a woman in Alabama was struck by a meteorite that crashed through her ceiling. It left her with a large bruise, but it did not burn her. These events show us that while their arrival can be dramatic, meteorites bring the cold of space with them, not the fire of their atmospheric entry. Let's turn our gaze to our closest celestial neighbor, the Moon. When you look up at its scarred and pockmarked face, it is easy to assume that every single one of those craters was carved out by a cosmic collision. For a long time we believed that impacts were the only story the lunar surface had to tell. However, we now know that this is not the complete picture. Many of the features that resemble impact craters are, in fact, the ancient remnants of the Moon's own volcanic past. The Moon was not always the quiet, geologically dead world we see today. The large, dark patches you can easily see on the Moon's surface, known as the lunar maria or seas, are perfect examples of this volcanic history. These are not bodies of water, but vast, flat basins that were filled with basaltic lava billions of years ago. These massive eruptions flooded enormous impact basins, burying older craters and creating the smooth plains we see today. Beyond these large-scale flows, the Moon is also home to other volcanic features, such as media group, close-up of crater chains on Moon, collapsed lava tubes on lunar surface, Erdi stock, distribute equally, crater chains formed by collapsed lava tubes, gentle slopes called lunar domes that are actually extinct shield volcanoes, and long winding channels known as rills, which were once rivers of molten rock. For a long time, scientists believed this volcanic activity ended billions of years ago. Recent discoveries, however, have forced us to rethink that timeline. Data from NASA's Lunar Reconnaissance Orbiter has revealed evidence of volcanic deposits that may be as young as 100 million years old. This means that volcanoes were likely still erupting on the Moon during the time when dinosaurs roamed the Earth. This discovery paints a picture of a much more dynamic and active lunar history than we ever imagined, with both external impacts and internal geological forces shaping the face of our nearest neighbor. Moving away from the Moon, let's consider another common misconception: the solar wind. The name itself suggests a gentle breeze blowing through space, but that could not be further from the truth. The solar wind is not wind in any sense that we would recognize it on Earth. It is not moving air. Instead, it is a constant, high-speed stream of charged particles, mostly protons and electrons, that are ejected from the Sun's upper atmosphere, the corona. This stream of plasma travels outward at incredible speeds, often between 300 and 800 kilometers per second, carrying the sun's influence throughout the entire solar system. A common question about space exploration is why astronauts float aboard the International Space Station. The myth is that they are so far from Earth that they have escaped its gravity. This is simply not true. The ISS orbits at an altitude of about 400 kilometers, where Earth's gravitational pull is still about 89% as strong as it is on the surface. If you could build a tower that high, you would feel almost your normal weight standing on top of it. The reason astronauts experience weightlessness is not due to a lack of gravity, but because they are in a constant state of freefall. To understand this, imagine you are in an elevator and the cable snaps. For the few moments you are falling, you and everything else in the elevator would be weightless. This is exactly what is happening on the ISS. The station and everyone inside it are continuously falling toward Earth. However, they are also moving sideways at an incredible speed of about 27,600 kilometers per hour. This immense horizontal velocity means that as they fall, the curve of the Earth drops away beneath them at the exact same rate. They are constantly falling, but they continuously miss the ground, locked in a perpetual dance of gravity and momentum we call an orbit. This brings us to another myth about space travel, that our probes journey to other planets in a straight line. It seems like the most direct route, but launching a spacecraft like the Voyager or Cassini probes in a straight line would require an astronomical amount of fuel, far more than we can currently launch into space. Instead, mission planners use clever and highly efficient curved paths known as transfer orbits. These paths are designed to use the least amount of energy possible by allowing the spacecraft to coast for most of its journey using the sun's gravity to shape its trajectory. To make these long journeys possible, spacecraft often use a technique called a gravity assist. This involves flying close to a planet to use its gravitational field and orbital momentum to gain a burst of speed, all for free. For example, the Cassini mission to Saturn performed 2 flybys of Venus, one of Earth, and one of Jupiter, to gain enough velocity to reach its distant target. The Voyager 2 probe used a rare alignment of the outer planets that occurs only once every 175 years to visit Jupiter, Saturn, Uranus, and Neptune in a grand tour of the solar system, a feat that would have been impossible without these gravitational slingshots. Let's venture out to the giants of our solar system, like Jupiter and Saturn. They are often called gas giants, which leads many to believe they are just enormous balls of gas, perhaps with nothing solid inside. This name is a bit of a misnomer. While their atmospheres are indeed vast and composed primarily of hydrogen and helium, these planets have complex, layered interiors where matter exists under conditions so extreme they are hard to comprehend. These worlds are far from being simple clouds of gas. They are places of immense pressure and temperature with distinct internal structures. If you could plunge into Jupiter, you would first travel through its gaseous outer atmosphere. As you went deeper, the pressure would increase dramatically. Soon the hydrogen gas would be compressed so intensely that it would transform into a supercritical fluid, a strange state of matter that is not quite a liquid and not quite a gas. Deeper still, at thousands of kilometers below the cloud tops, the pressure becomes millions of times that of Earth's atmosphere. Here the hydrogen is crushed into a form that does not exist on our planet, liquid metallic hydrogen. This electrically conductive layer is what generates Jupiter's incredibly powerful magnetic field. At the very center of this colossal world, scientists theorize the existence of a solid core. This core is thought to be composed of rock and ice, with a mass perhaps 10 to 20 times that of the entire Earth. The conditions here are truly mind-boggling, with temperatures hotter than the surface of the sun, and pressures reaching 45 million times that of our atmosphere. So, while we call them gas giants, a more accurate description might be worlds with a small, gassy exterior surrounding an immense, exotic ocean of liquid hydrogen, all wrapped around a solid, superheated core. Finally, let's travel to Mars, the red planet, famous for its planet-encircling dust storms. Movies like The Martian depict these storms as ferocious tempests with winds powerful enough to destroy equipment and flip spacecraft. While Martian dust storms can indeed become global, covering the entire planet for weeks, the wind itself has very little force. This is because the Martian atmosphere is incredibly thin, with only about 1% of the pressure of Earth's. A 100 km/h wind on Mars would feel like a gentle 10 km/h breeze on Earth. It certainly could not knock over an astronaut. The real danger is the dust itself, which is as fine as flour and gets everywhere, blocking sunlight from solar panels and clogging sensitive machinery.